How to graph y equals the cotangent of x using the unit circle values and with proper vocabulary. This is part of the Family of Functions series. You will need paper and a straight edge, or you can download this PDF and print it. Press pause as needed anytime during this video. Graph y equals the cotangent of x. Note we are proceeding with the assumption that students know the unit circle values for the cotangent function, its domain, its range, and where the cotangent function is undefined. We will plot the cotangent function from x equals -pi/2 to 2 pi. Pause is needed. Resume when you're ready with your grid setup. First, we'll draw dashed vertical lines where the cotangent is undefined. Since the cotangent is the reciprocal of the tangent, or we could also write it as the cosine of x divided by the sine of x, the cotangent is undefined when the denominator is 0. That is, when either the sine or the tangent is 0, and there happen to be 0 at the same places. We're going to look at the sine function. It's 0 at these three spots, 0, pi, and x equals 2 pi. In fact, it's undefined at any multiple of pi. So we're going to draw dashed vertical lines where this is undefined, beginning with 0 pi or 0, x equals 0, x equals 1 pi or x equals pi, and x equals 2 pi. Next, we're going to plot points from the first quadrant with a table. Here's your table. Pause to complete the table. And these are the values that we came up with. Notice that we're going to have to get decimal approximations for these two irrational numbers. And so I have an 84 and Inspire, however you want to get your decimals, and we're going to round it to the nearest hundredth. Pause is needed. So here's our approximate values. We're going to go ahead and plot the points. At 0 it is undefined, so there are no points to plot. At pi/6, which is 2 pi/12, up to almost 1 3/4, 1.73. Pi/4, 3 pi/12, up to 1 exactly. Pi/3, about 0.6. And at pi/2, exactly 0. Let's look at values of x that are close to 0, but positive. We'll talk about numbers right here. See what's going on with the cotangent function. For example, if x were to be 1/10, which is close to 0, but to the right of 0, we use a calculator here, and the cotangent of 1/10 radian is about 9.97. We'll get a little closer, like maybe 100th. And the cotangent of that is 99.997 approximately. And one more, maybe 1,000th. And the cotangent is a lot bigger number. And you can see there seems to be a bit of a pattern here. So from this table, it's clear that as x gets close to 0, closer and closer to 0, but greater than 0, cotangent is getting larger and larger. So let's go ahead and connect the points now. In fact, for emphasis, we're going to extend that asymptote up a bit so we can see that as x gets closer to 0, this green gets larger and larger, closer to the asymptote without touching it. But let's look at that a little bit more. Let's analyze what's happening to the graph of y equals cotangent of x as x is close to 0 or approaches 0. From the right side, because we could just also approach from the left side, but we're going to look from the right side. And our shorthand notation is x arrow 0 and then a plus sign for looks like in the exponent. And this means that x is getting very close to 0 from the right side, or this means that x is approaching 0 but strictly larger than 0. Pause is needed. So let's analyze the cotangent graph as x approaches 0 from the positive side. The cotangent is cosine of x divided by sine of x. So we're going to look at the cosine and sine graphs. Here they are. Now the cosine's in the numerator, and as x gets close to 0 but larger than 0, the cosine is getting very, very close to 1. For example, it could be like 0.999. That's pretty close to 1. And as x approaches 0 here from the positive side, the sine is getting very, very close to 0, but positive. On the other side it would be negative, but this side it's positive. So let's go with maybe 1,000th, 0.001. So when we go to divide those two numbers, that's like dividing 999 by 1, which is 999. So when x gets closer and closer to 0, this number is really, really large. Another example, the cosine could be 0.9999, really close to 1. And the sine could be also close to 0, like 0.00001. And when we divide those two numbers, we get a much whopping big number, 99,999, which is almost off the charts. So generalizing here, as x approaches 0 from the positive side, the cotangent of x is increasing without bound. That's the phrase we're going to say. Increasing without bound, getting so large, so fast, the closer we get to 0 from the positive side. And the line x equals 0 is a vertical asymptote, or a boundary line. Pause is needed. Next, let's plot points from the second quadrant with a table. So here are our values from the second quadrant that we should know. Pause to complete. And these are the values, and then we'll put in the decimal approximations. Those are all negative in the second quadrant. Plot the points. Pi over 2 zeros there already. 2 pi over 3, which is 8 pi over 12, down about negative 0.6. 3 pi over 4, down exactly 1, negative 1. 10 pi over 12, 5 pi over 6, about negative 1 3/4. And at pi, it's undefined. Now, using similar logic as we did in the first quadrant, we're going to connect the points. And instead of going up to the left infinitely, it's going down to the right infinitely. And let's look at what's happening to the graph as x gets close to pi, but from the left side a little smaller than pi. The shorthand notation for this is x arrow pi with a negative sign as the exponent. This is read x gets close to pi from the left. Or we could say x approaches pi, but it's smaller than pi. So as x approaches pi from the left, the cotangent is decreasing without bound, is the phrase that we're going to say. Decreasing without bound, getting very, very large, but in the negative sense. Pause is needed. Recall that the period of the cotangent function is pi. And we've graphed a period from 0 to pi is pi, so we have a full period there. So all we have to do is just duplicate the graph. So here, this will shift over here from pi to 3 pi over 2. This will shift from 3 pi over 2 to 2 pi. And then going backwards from negative pi over 2 to 0. And this is what it looks like more beautiful. The domain, well, it looks like it's all real numbers, except where the cotangent is undefined. The cotangent function is undefined where the sign is 0. This is at multiples of pi. For instance, 0 pi, or just x equals 0, x equals 1 pi, x equals 2 pi. So using math symbols, how would we write this? We write it the set of all x such that x is a member of the real numbers. X cannot equal k times pi, where k is an integer, meaning like 1 times pi, 2 times pi, negative 1 times pi. Those values are all taken out. It's all real numbers except these. The range, well, it looks like it's going on infinitely in both directions, positively and negatively. So it seems to be all real numbers. You can see it's going on infinitely, all the values there. So we usually write that with a script R. The range is all real numbers, and this is the symbol that we use.